Okay, so this is, oh, sorry. Okay, this is lecture 22. So first of all, let's come back to our previous lecture material, lecture 19. So in this slide, now you can see the general landscape of DTCO, Design Technology Co-Optimization, especially from the viewpoint of TCAD. In this case, you can find that we have already covered some things related with process simulation, and we have covered also device simulation. So if we wanted to cover the entire DTCO toolchain, then the next step will be, of course, this compact model. But unfortunately, as you can see here, now we are already in lecture 22, and we have only 4 remaining lectures, but the last 2 cannot be made on offline, so on site one. So I will just wrap up our lecture like this. So today we will cover one example, typical example of how can we optimize our transistor with TCAD simulation, and 23. So we will have the last on-site lecture, and after that we will have 2 additional one. So that will be next Monday, and that will be next Wednesday. And here we will cover the remaining topic not covered in our lecture, and the last one, so that will be just a review of a DTCO paper in IDM 2025. We have several DTCO papers in IDM, so we will just I will just show some selected ones, so that can be a good wrap up material for our DTCO course. So simply speaking, although the entire complete DTCO toolchain requires 2 additional capabilities. One is how can we build compact model, and another one is how can we extract parasitic resistance and capacitance from given structure. And after that we can run simulation with these extracted compact model and parasitic RC network. So that can be entire tool chain or workflow. However, we have covered only this part, so therefore if you wanted to perform your term project, then please concentrate on these 2. Using only these 2 tools, please try to make your homework, no homework, or term project video. And what I wanted to show you today is one typical possible example of how can you utilize these 2 tools to make a certain analysis. So let's just quickly go to this one. Okay, so our goal is in this short presentation, the goal is quite simple. What is the role of gate length on device performance? So let's just consider this one. We have CPP. In this case, in our currently available technology, CPP is 54 nanometer, and when we decompose it into different parameters, we can make it into some of these 3 parameters: LG, gate length, and spacer length. It's twice, and source drain length. So if we make the top view, then of course here we have LG, and there we have spacers. Yes, this is L spacer, and also we have another L spacer. That's the reason why we have a free factor of number 2. After that, we have also a certain range assigned to our source and drain. Yes, LSD and LSD. However, pitch, so contact poly pitch means that the period of a repeated pattern, so the entire LSD is not considered. Actually, we start from this half position of LSD and end at the same pattern in this LSD. That's the reason why the entire CPP value is made by this simple expression LG and spacer length twice and source drain length. So in our typical example, we have considered in this ASAP model, it was 20 if I remember correctly, and that was 9, so we have 38 already, and this one was 16 and 16, so half of it, 8 was assigned to each device. So let me just read this one. When the CPP is fixed, so usually we fix the CPP because who decides the CPP? Because in order to reduce the chip area or cell area, we need to reduce CPP, because CPP in this layout plane, CPP is regarded as this horizontal unit of length scale. So if we reduce CPP slightly, then also we can reduce the size of our chips slightly. So CPP is not determined by actually technology guys, but requested by our designers or customers. So when CPP is fixed, for example, for 54, then we must decompose it into 3 parameters. Yes, and now you understand we can make it in this way, but there are pros and cons of scaling each parameter. For example, let's say that we have scaled gate length, so LG decreases. Good, because if we just reduce the length, then we believe that our drain current has a free factor of 1 over LG component. So since the channel is reduced, the distance for our electrons or holes to travel becomes shorter, so it increases the current of our transistor. The channel conductance may improve, but at the same time, of course, we suffer from severe short channel effect. So reducing gate length seems to be a good solution, but maybe there can be a limitation. So if the further reduction of gate length scaling is not beneficial, then we must stop. Then where we should stop? That is the question. And also another one is L spacer. If we have longer and longer spacer, then yes, so spacer, this one, and if we have a longer spacer, then yes, then it is always good to have this long spacer in terms of capacitance, because here we have a source and here we have a gate, and far away there drain. So if this distance becomes higher, then source to gate parasitic capacitance can be reduced significantly. So that is good. However, also when we reduce a spacer shorter, then short channel effect may occur, and also in terms of capacitance, it's not a good one. So it is always good from the viewpoint of electrical properties. We need to have a sufficiently long spacer, or thick spacer. However, problem is this one really consumes our CPP, and significantly, because here we have a free factor of 2. So if we increase spacer by 1 nanometer, then that will introduce 2 nanometer increase of our CPP value. So although we wanted to have a spacer level as thick as possible, but it is not good from the viewpoint of area consumption. And finally, we have LSD, yes. And if that decreases, then of course good for reduction of CPP, then source drain resistance increase. Yes, you may think that, okay, source drain is highly doped, so maybe that doesn't make a big difference in performance, but unfortunately it's not. Nowadays, since the scale of source drain is so short or so small, so the change in LSD can introduce significant differences in our device characteristics. Even more important thing is LSD does not define only our silicon part. For example, let's say that here we have a diamond here. Yes, we have a diamond, and reduction of this LSD length means that we have a shorter LSD. But another one is, on top of it, we make salicide, and on top of that salicide also we introduce via, so connection from metal 0 to this internal device source drain. So since this length is now shorter, it means that not only doped source and drain region, but also via size is also reduced and becomes more difficult to reliably manufacture this structure. Of course, in this process emulation, we cannot see what is possible or what is impossible in real manufacturing. However, we can expect that if we reduce a certain scale quite aggressively, then that will make some problems about the real fabrication process. So, simply speaking, everything has some pros and cons in terms of electrical property and manufacturability. So, that's the reason why our job is to make a certain compromise between these pros and cons. Okay, so that will be done in our example today, but I cannot cover all of them, just to show one part, so mainly concerning the LG part. And please note that when I say LG equal to 20 nanometer, so LG equal to LG equal to 20 nanometer, my convention is just to dummy gate length. So what is this? We first define dummy gate. After that, when we really makes our gate stack, first of all we make a interlayer. For our FinFET, let's say that there is fin, then we just let's say this is fin, our fin, then we make a very thin, extremely thin silicon dioxide layer, and after that we just deposit our high K layer all over this structure. So not only on this silicon dioxide, of course we have some here, however now here we have a spacer, but even near the spacer we can have high K layer. So in this case the thickness is only high K layer, and in this case the thickness is interlayer and high K layer. So although we say this number equal to 20 nanometer, in reality the place where actual gate consume should be given by 20 nanometer minus 2 times of high K layer thickness. So in our example we have made a quite inaccurate assumption, like all of our dielectric layer is just 1 nanometer thick pure silicon dioxide. In reality our high K layer thickness is not 1 nanometer, it is about 2 nowadays, and previously it was about 3 nanometer. So we must consider that the actual gate length is even shorter than our current calculation. So in our case we have to say that in our example structure we must consider minus 2 nanometer for actual metal gate length from the drawn dummy gate length. So 20 means that actually 18. So when I say 10, then it is corresponding to actually 8. Okay, so please understand. Actually, in terms of 20 nanometer long, then may not a big deal. Actually, that is a big deal, but that is not significant. But let's say that if we go down, for example, 12 nanometer, 12 and 10, that makes a real difference. And as you know, high K is not 1 nanometer thick. It is at least 2 nanometer thick. So if we go down to 12 nanometer drawn length, then it is corresponding to really 8 nanometer long gate length. So nowadays when we say gate length, actually we must consider the real gate metal length, not the drawn dummy gate length. Okay, please be aware of this difference. But right now I will just use this convention. Okay, so as much as we apply certain convention consistently within our work, then it is okay. But please do not shake any convention during your certain job. And other geometric parameters are fixed. It means that most important one in this case is a fin shape. Among fin shape, we just keep 7 nanometer thick fin. If we reduce fin thickness down to 6 nanometer or 5 nanometer, then its short channel immunity can be greatly improved. So you will see it. If you want to have, then maybe you can try. But we will just keep this fin shape because this is not usually not available to designers. Of course, this kind of for example, CPP option is not also available to designers. But anyway, I will just keep this fin shape 7 nanometer, and also 32 nanometer fin height will be fixed. So that is my assumption. So if you want, maybe you can change its shape, then give some improvement or worsen behavior of your performance. So also no calibration for material parameters. Okay, so I will explain it of 1 minute later. Here we need to something. Fin just looks like this, 32, 7, 32. So its aspect ratio is like 1 to 4 or 1 to 5. So it's not that tall. But what I wanted to say is when we have this kind of a fin, then the usual way we normalize our drain current is given by this effective width. So here we have a interface, a silicon and silicon dioxide interface, 32 and also 32, and here we have 7. So simply speaking, 32 plus 7 plus 32. So in total, 71 nanometer is typically regarded as effective width of this transistor. Okay, although it is drawn in, if we just have a look at from the top, then it is formulated just within 7 nanometer. However, due to the existence of these two side walls, side channels, and we have to consider 71 nanometer wide device. So that is really good thing, because we can save our silicon area significantly, but internally we can have quite a large area for collecting our electrons or holes. This is the typical way we do. So simply speaking, if you have, for example, 1 nanoampere as your drain current, then when you report your current, then maybe you can just say that per pin, the current is 1 nanoampere. That is one way. However, in many cases, people just wanted to have a normalized value. Then what should be the normalizing length scale? In this case, this effective width 71 nanometer or 0.071 micrometer should be used to consider this kind of calculation. The reason why I'm talking about this one is quite interesting. Nowadays, people are no longer using FinFET, and they are using, I mean that of course they are using FinFET in mass production, but in R&D, then they are using this gate-all-around transistor, especially multi-stacked. For example, let's say that there is 5 nanometer thick silicon slab, and say that this is 20 nanometer wide, and let's assume that there are 3 stacks here. 3 layers are coexisting inside one single device. Then if we are asked to calculate the effective width of this transistor, what will be your answer? Obviously, you would say this one has 5, 20, 20. So therefore, one single stack contribute 50 nanometer. And also here you have 50 nanometer and 50 nanometer. So in total, in this device, we have the effective width of 150 nanometer. That is the case we have actually in this multi-stacked gate-all-around nanosheet transistor. However, when you normalize, when you report your current in this gate all around the transistor, we do not typically use 150 nanometer as the normalizing effective width. Instead of that, we just report this 20 nanometer, the drawn width of our nanosheet seen from our top view is effective width here, 20. So compared with this 150, this 20 just says that 7.5 times smaller. So now you can expect that if we really use this 20 nanometer for normalizing constant, then we can report or we can generate a lot higher value for our normalized current. So is it a fair comparison between FinFET and nanosheet MOSFET? I don't think so, but this is the convention. So please do not be fooled by really high values of reported normalized drain current when you have a look at gate all around the transistor. This is the real convention we are currently used in the industry. So in the case of FinFET, if we really use number 7 as the effective length, then that will contribute a lot of higher value, and the actual channel is hidden in this scale. So if you say 32, 64, in this case it does not contribute to anything to this change. So if that is 7, although you have increased the fin height by twice, then you can increase your effective width twice. But if you just report just number 7 fin thickness as effective width, then it does not consider the change of the real change in our case. However, in the case of a nanosheet case, actually the thickness of a transistor or thickness of a channel layer is more or less given as a 4 point something or 5 nanometer. So it is given. The designer can just change the width of this drawn width of our transistor. So it is really corresponding to the change of our transistor properly. Only the exaggeration comes from this additional factor of 3. So this additional factor of 3, then why don't you just consider single device, single step? But it is not a fair comparison because this top, middle, bottom, 3 stacks does not or do not perform equally. So we have to consider the combined effect of these 3 stacks. So therefore, that is a convention. So please just accept this convention and be aware of differences in normalizing constants. Okay, so that was my warning about normalization. So, and here let me just come back to this line. No calibration for material parameters. What does it mean? If we go to really short channel device, already like 20 nanometer is quite short, or even shorter, then actually our model, among our physical models, mobility models, especially the one named as canali, so corresponding to the velocity saturation, actually it fails. So this canali model cannot provide us the proper level of a current value. So usually the tendency is if you adopt this canali model with default parameters for this is such a short channel device, then usually you underestimate your current. Because if we have a really short channel device, let me just explain just qualitatively, not quantitatively, but I think that is important too. Here we have certain system. Let's say that this is a source and drain. Of course, we have an energy barrier between source and drain. That's the reason why our current does not conduct and when we apply low gate voltage. Problem is, now we increase gate voltage. Then it means that the energy barrier between source and drain is now reduced, then we can expect current conduction. So electrons are injected into this channel region. After that, it is accelerated. Why it is accelerated? Only because we have applied higher VD than Vs source value. So since it is negatively charged, so it is accelerated or drained to the highly biased region. So there is an acceleration. But this acceleration is not perfect, and if we arrive at certain saturation velocity, then the electron velocity does not grow higher than this saturation velocity. That effect is considered in this canalic model. But problem is, now we have a really short device. Now we have a really short device, and the mechanism to support this saturation phenomena is sufficiently large number of scattering events between electron and scatterers. So if its speed, electron speed goes to too high, then there occurs higher chances of scattering event, and its speed, velocity goes down to this saturation level. Whenever this driving force, the highly biased drain, try to accelerate our electrons even higher. However, if it arrives at high velocity regime, then now it has higher chances to be scattered. So are you with me? So let's say that maybe you have already enjoyed such kind of game, amusement part. So let's say that there are holes and something pops up, then you just punch it, then it come back and pops up, punch it. So if nothing is popping up, then there is no punch. However, if there are many pops, then you will have many punches. So eventually, if we make just a snapshot of these holes, then what will happen? So maybe you can find that the average height of holes will be just maintained slightly over this punching line. So this is the threshold or criterion for punchy or not. So that will determine the eventual height of these holes. So simply speaking, it is quite similar like this. There is a certain saturation velocity. If electron velocity exceeding this level, then suddenly it becomes very proactive to scatter this electron and come back to the lower velocity regime. So that's the reason why we have a velocity saturation. Now you understand, in order to keep this trend, we have to have sufficient length and time to have the scattering event, and sufficient chances are required. However, this is so short. So therefore, speeding electrons can arrive at drain even without caught by scatterers. So let me just give you another analogy. There are long road and there is a car. This car is speeding, and there are many police cars here and here and here, and let's say that this is so just 60 kilometer. And now let's say that if I ask you whether this guy can really speed during this 60 kilometer long, so your answer will be, of course not, because when it getting closer to this police car, then it should de-accelerate down certain speed limit, and after that also before this one comes, then accelerated and de-accelerated, accelerated, de-accelerated. Therefore, the overall speed cannot, not that much that of this speed limitation. But instead of this 60 kilometer, just to say there is only 100 meter between starting point and the ending point, then what will happen? This guy, so quite brutally accelerated his or her car to arrive at 100 meter away the target goal. So that is the situation from the viewpoint of our electrons. Now when we have quite a short distance between source and drain, then it can exceed the saturation velocity set by this phenomena, and now we can expect that the current of these electrons can exceed saturation velocity. However, that is not that well expressed or described in our canali model. The best thing we can do is just to calibrate this saturation velocity parameters according to the different structures. For this structure, we apply slightly higher saturation velocity. Even shorter devices, we can apply even higher saturation velocity. Higher saturation velocity means that actually becoming more ineffective in terms of velocity saturation. Or then maybe you can ask me this question. If that becomes so ineffective, why don't you just eliminate this model? Then it means that we completely neglect this velocity saturation effect and becomes free from it. But unfortunately, it's not. It really introduces a huge impact in our calculated result. Without this kind of velocity saturation effect, we never achieve the proper level of current value. The thing we have to do is careful calibration of saturation velocity. So that is the problem. So we must understand the limitation of our calculation. Although we have tried to simulate quite a short channel device, but our saturation velocity is more or less just 10 to the 7 centimeter per second, the default value of our electrons. So this one is somewhat lower than the measured one in our real devices. Okay. And finally, in this structure generation, I just assumed the perfect contact alignment. In our previous calculation, we intentionally introduced 5 nanometer or 4 nanometer misalignment in our contact alignment, but now contact perfectly alignment. What does it mean? Here, previously we had a slightly misaligned one, but we make a perfect alignment. So now let's have a look at this one. In this example, we just set spacer length as 9 nanometer. It is fixed. It means that since spacer, 2 times spacer is required, 18 is already consumed by our spacers. So it means that we have to have this sum. Gate length and source drain length should be 36 nanometer, and this 36 should be divided into 2 parts. If I take 20, you take 16. If I take 10, then you take 26. There is the zero sum between these two parameters. So we will take this scenario. So list of simulated LG values starting from 20 nanometer. So let's assume that this is the baseline, and I just reduce it down to 10 nanometer. Actually 10 nanometer means that the metal gate is only 8 nanometer. So in reality it is almost impossible to have this kind of thing. Why we don't have this kind of thing? This device can be really made. We can make 8 nanometer long channel in real fabrication. But before talking about any kind of electrical property, something like that, but already in 8 nanometer long channel device, actually tunneling occurs between source and drain. Source and drain are so close, so we can have a we can have the source and drain tunneling. Also, it sensitively depends on the doping profile. So source and drain doping profile. But anyway, that is not feasible in reality. But let me just start. So also we have not included any kind of a tunneling effect in it, so our result does not consider that kind of a direct source to drain effect. This one is corresponding to LG equal to 20 nanometer, and this one is corresponding to LG equal to 10 nanometer. You can see that the size or length in this scale is the same, 54 nanometer, and there is the real zero sum. So now this one becomes really shorter, and instead of that, now we have much wider this source and drain region. So if this source and drain region resistance becomes a big problem, then certainly this one will be beneficial to reduce source and drain resistance. But in this example, mainly the current is determined by the channel. So let me just see the result. So I'm just showing you the data for our default device, the baseline device of gate length 20 nanometer, and just set work function of something. But actually work function in this case, it's not that important. I will explain the reason. The reason why it is not that important is I think that my presentation material skip one important. Yes, here we have an important statement. Please try to measure on current under the assumption of constant of current. This is the real thing we have to do. In the previous lecture, although that was pre-recorded, then we just have seen something corresponding to the simulation, and I just gave you some example, and it had certain off current and certain on current, and if you change your parameters, then we have different values. But in order to make the real fair comparison, the typical way is keep the I-op as the same value. That is the key point. Then maybe you can ask me this question: how can you keep this op current at a given position? In order to keep our op current at a given value, we must have some ability to change our effective work function properly. If, for example, let's say gate voltage and drain current, and let's say that this one is 1 nano ampere, and say that our curves, actual curve, just looks like this in this semi-logarithmic scale. So this is a logo of ID, and now we have a straight line. So we wanted to have this curve. When gate equal to 0, our current should be 1 nanometer. However, we simulate, and it says that actually when gate equal to 0, your current is somewhat lower, and in order to have this exactly 1 nano ampere, then you have to have a certain amount of, for example, 0.1 volt should be applied to your current simulation depth. Then what we can do is just to shift our work function. So then can we change 0.1 EV change in our gate work function quite properly? So we assume that device engineers has some capabilities to shift their curves by adjusting their work function and metal stack. So that is our assumption. Just to run your simulation with a certain reasonable value of gate work function. Then you will have certain curves up from or far away from your required op current condition. Then assuming that we can adjust work function just to parallelly shift it to this condition, then you will have the I-on under that case. So let me just give you that example. Here you can see that, let me just follow 1 nanometer specification. I think that my drawing is not that good, but anyway, this is a more or less a parallel line. So this is corresponding to our 1 nano ampere case. So simply speaking, this is corresponding to your gate voltage equal to 0 volt, means that when you apply gate voltage equal to 0, your current is not exactly 1 nanometer. So we need to actually our simulated curve by amount of this negative direction. So I just manually find out how much we shift, and its value was about 16 millivolts. Yes, if we parallel shift our curve by amount of 16 millivolt, then we have 1 nano ampere op current. So instead of reading the value, I-on value at gate equal to 0.7 volt, instead of that, I just read 0.716 volt. Then that is the way to collect this corrected on current for our case. Okay, so yes, so of course in this case I used this linear approximation between curves. In this case logarithmic, and in this case linear. So anyway, if we take this corrected on current under the given off current constraint, now we have 35.2 microamp. Or if we normalized it with effective width 71 nanometer, then we have values about 500 microamp per micrometer. So now let's go to the gate length of 10. Obviously this one is corresponding to gate length of 20 nanometer, and this LED one is corresponding to 10 nanometer. And as you can see, when we have a gate voltage of 0, previously there was a certain value, and now we have values much higher than that, almost about two orders of magnitude higher, not exactly, but roughly speaking, we have 2 orders of magnitude higher current value. Why do we have such a high of current? It is quite obvious, because Schwarzschild effect. So now, although we wanted to shut down our transistor by applying 0 gate voltage, but since this device, this 10 nanometer device, suffers from Schwarzschild effect, it cannot prevent the current conduction. So we have quite a high of current. It means that, in order to this 1 nanoampere becomes the values for 0 volt, then we must parallel shift once again this LED curve toward this positive direction. About 0.1 volt shift is required. So it means that instead of gate equal to 0.7, we must lead the values, the drain current values at 0.6 volt. Once we read 0.6 value at this LED curve, then this LED curve is shifted by amount of 0.1 volt. Then now op current is matched to 1 nanoampere, and this value now in this shifted curve, it becomes 0.7 volt. So now you understand the importance of this op current matching. So according to this procedure, if your op current is too high, then actually the gate voltage we use in our calculation is much reduced than our correct VDD value. So due to this severe Schwarzschild effect, now you can see that the corrected ion value shows 22% reduction. So that cannot be understood. So you cannot have 22% reduction of your own current within this same structure. So obviously this is quite a bad situation for your technology. So I think that this is the last slide of our today's lecture. So let me just draw on current corrected with the same op current 1 nanoampere as a function of gate length. What I did was, first of all, generate several devices, 6 devices, and run them all, and just to measure op current and from that op current, then I just calculate how much we must parallel shift our available curve. After that, measure the on current at this corrected gate voltage. This one shows that trend. Starting from our baseline 20 nanometer, if we reduce this gate length, then what usually we can expect is, oh, since we have reduced our gate length, so following 1/LG relation, maybe our own current would increase. That can be a naive consideration. However, if we consider more realistic one with ISO op current condition, so then you can see that if we increase or decrease gate length, then there is a rapid reduction of our on current condition. So simply speaking, we should not reduce our gate length. We must keep this value. So in this case, the slope is quite not that steep. So now you can see that maybe there in this part maybe there is a flatter here. Please have a look at this one. If we don't make any kind of a correction, if we just report on current at Vg equal to 0.7 without any change, keep the value and report it, then you can find that starting from this 20 nanometer, it actually goes up. Not like twice, but slightly increased value is obtained. However, it does not show that actually this device performance is improving, because this increase is related with severe degradation of our op current performance. So if we just keep the same op current, then the actual drivability goes really down. So that's the reason why we should not have too much scaled device. So that's the reason why. So in this case, we have a certain limit of our short channel immunity, and that's the reason why our CPP has a certain minimum value. We must have a certain minimum value of source and drain, certain minimum value of gate length, also certain minimum value of spacers, and combining them all, then we cannot reduce our CPP any longer. That's the problem. And then how can you do that? So of course, engineers can try many different things, and they can introduce many clever ideas. However, I want to state one point. Although they can make clever ideas and some tricks to slightly improve the performance, but more or less this short channel effect is a kind of electrostatic problem. Short channel effect is not determined by our effort or our ambition, our investment. It is almost solely determined by the shape of our gate channel. If our channel has more coverage by gate, then it will have a better short channel immunity. If we don't have less coverage, then it is true that we have a lower or worse short channel immunity. So that's the reason why nowadays people have tried to improve multi-gate transistors. And for example, in your project, maybe you can try to make a comparison between two different architectures. For example, FinFET and gate all around the transistor with similar sizes. So what is a similar size? It really depends on you. For example, let's say here we have a FinFET, which is 7 nanometer and 32 and 32. Of course, it has a sub-fin and STI, but let's just say that you are now trying to simulate a 7, 32, 32, 7. This is gate all around the transistor. Then, in terms of its effective width, maybe they are equivalent or quite close to the equivalence. However, can you say they are equivalent in terms of layout? This guy just consumes only 27 nanometer fin pitch, and this one already consumes 32, and also we need to introduce also certain range for covering this metal, and also in order to introduce another stack here, so this is a parallel one, we have to introduce also certain distances between them. So it can have a metal, and also this guy can have metal, and between them we must also introduce isolation. They should be isolated. So from the viewpoint of sizing, so obviously this guy has much less beneficial than this FinFET. Actually, that's the reason why in our current implementation we do not introduce this single stack transistor in order to compensate the obvious disadvantages in our area consumption. So we introduce more stacks. So although it consumes quite a large area, however, it has multiple copies of silicon stacks, so that can increase the drivability. So that is the one. So therefore, if you perform your own term project, then you must first of all decide what is apple and what is an orange. So you should have the fair comparison. Then you should have your own justification why these are equivalent in terms of some point of view, and then within this fair comparison consideration, now this guy shows a better short-channel-ability, or this guy shows a worse one. So that can be your analysis. So anyway, now the semester is going to its end, and now if you have not started already, then you must start your term project. Your almost your final score is almost entirely determined by this quality of your submission, so term project submission. So please concentrate on this one. Okay, do you have any question about the lecture contents or term project? Okay, so I have not yet thought about that one, but let me just let's discuss. Here, it's today, and it is our next lecture, and this is the end of our on-site lecture, and you will have 2 more pre-recorded lectures, and this is reserved for our final examination, but we don't have any final examination. So usually what I allow is this date, 22, and as usual, morning 8 o'clock. So now I think that it is quite our typical deadline. So you can have you maybe you have other final examinations. Maybe concentrate on this one, and please use our weekend to finalize your term project. Okay. Submission is not as a form of a report, not LMS submission. Please directly send me your recorded video. Then I will upload it our YouTube channel, and also based upon the quality of your video presentation, so I will give you the final score. Of course, we have attendance check and homework submissions, but all of you are doing quite well. So in many cases, your homework scores are quite high. So there is no differences. So please, and although this DTCO is the very first one I tried, but in my YouTube channel you may see other different courses. In other different courses, our former students submitted their term projects, and please follow similar way. There is no limitation about video length. So longer one is also acceptable, and shorter one is also acceptable. I remember that there was about 3-minute long or 5-minute long one. I was actually a little bit astonished, but anyway, that is allowed. So don't give up. Just a submission or failure of a submission makes a big difference. So please do your best to prepare the final term project video. Okay, good question. And I will just make the official announcement once again. Although we have discussed or I have announced the final submission deadline, December 22nd, 8 o'clock in the morning. However, I will make another one email notification. And do you have any other questions? Okay, if not, then let me just conclude today's